Hey you guys, uh, welcome back. This is Unit 5, Notes number 1, okay? Um, just a preface here, this lesson is a little bit more condensed because this was supposed to be covered in the first semester, so apologies if I'm rushing through this, but you're going to get the shortened version of this, okay? Now, if you're ever curious about it, you could always ask more questions, okay? So this goes along with the PDF that I sent to you guys. As of now, if I did not send it to you, text me right away so I can send out a mass text, okay? All right, so what we're going to do here is we are going to revisit some of the theorems that we've covered, and we are going to explore the last two theorems that we haven't covered yet, okay? And then I'll show you guys how you might see it on your AP exam, and then what you can do to easily remember it, okay? Okay, here we go. So write it as you go. Feel free to pause whenever you'd like. When I ask you guys to think about it and pause, actually do it. Don't just wait for the answer because you want to be able to kind of let your mind go through the process of the thinking, okay? So just keep that in mind. Okay. There were 4 existence theorems. We call it existence theorems because it's theorems that guarantee that something will exist. Okay? The first one we covered was, here we go, IVT. Okay? Feel free to look back if you guys need to. Think about what that stood for. Okay? This was the intermediate value theorem. Okay? Now remember, intermediate, if you're a gamer, you know intermediate means middle or somewhere in between, right? This is where I gave you guys that example of the birth height scenario. Okay? Pretty much what you're guaranteed here, and feel free to pause if you want to figure it out on your own, but you're pretty much guaranteed to hit all values in between, okay? And this is a very loose way of writing the theorem, okay? Then you're guaranteed to hit all intermediate values, okay? So for instance, if you were born at 17 inches tall and now you're currently 6 feet, somewhere throughout your life, you would have hit every single inch in between 17 inches and 6 feet, okay? So this is only possible if f is continuous on a closed interval from A to B, okay? Again, this is a very loose way of writing the theorem. So when you guys see IVT intermediate, think about in between, all the values in between, okay? All right, EVT. Go ahead and revisit that if you need to. Pause here and press play whenever you find it back in your notes, okay? EVT is the extreme value theorem, or as I like to call it, the Extrema value theorem, okay? This pretty much guarantees you a high and a low, okay? You're guaranteed at least one absolute, max, and min. You're going to get at least one of each. You could get more than one, okay? And again, this is only possible if f is continuous on a closed interval from A to B. Okay, so for instance, if I were to draw any continuous function on a closed interval, notice how the lowest point exists and the highest point exists. Okay? And also the intermediate value theorem states that you're going to hit every value in between your 2 points. Okay, that's IVT. EVT just guarantees that you have a high and a low. All right, and this is only possible assuming that your function is continuous on a closed interval. So notice right away how there's a pattern here. The moment you know that a function is continuous on a closed interval, IVT and EVT comes into play. Okay? Okay, now the next one here is MVT. All right? MVT, we're going to go ahead and call this the mean value theorem. Okay? Mean stands for the average, okay? And I'm going to draw you guys a picture to kind of just illustrate this in your head here, okay? So just think about a driving scenario. Okay. So let's say that the curve I'm about to draw you represents your speed going from your house to Disneyland, okay? And this is inaccurate, all right? Let's try this one more time. Okay, so this represents the speed at which you're driving to Disneyland. Let's assume that there's no traffic and no lights, okay? Just to make it a little bit simpler. So here, since we have 2 points, if you guys remember, with 2 points, you could find the average rate of change. Okay, so your average speed, I'm going to go ahead and say your average speed is 65 miles per hour. Okay, what the mean value theorem here states is if your average rate of change is 65 miles per hour, then there has to be at least one moment where your instantaneous rate of change is exactly 65 miles per hour as well. So if you guys recall, instantaneous rate of change is a tangent line, okay, or the slope of a tangent line. So you're guaranteed to find at least one moment where the instantaneous rate of change, or I'll call it IROC, is exactly 65 miles per hour as well. So think about this logically here. If you drove an average of 65 miles per hour, there has to be at least one moment when you're in the car and your speedometer reads 65 miles per hour. Because you might have gone a little bit faster and a little bit slower to get an average of 65 miles per hour. Okay? So there's at least one moment where that little speedometer meter crosses 65 at least once. That's basically what MVT is here, okay? So notice how the secant line and the tangent line have the same slope, okay? Another way of thinking about this is that when you have the same slope, you call it parallel, okay? So basically, here's what we have. I'll fill in the if part afterwards, okay? So leave a lot of space there. You're guaranteed one thing, but we can write it in 3 different ways, okay? You're guaranteed basically where your secant line is parallel to your tangent line. Okay? In other words, your average rate of change is equal to your instantaneous rate of change. Okay? In other words, instantaneous rate of change is the derivative. So we write it as f prime. In this case, I'm going to use c. C represents there's a moment in between, okay? Now, average rate of change is pretty much the slope between 2 points. And the fancy way of writing that is f of b minus f of a all over b minus a. Okay, so just to make sure that we understand where this is coming from. This is basically if you have a point a comma f of a and then b comma f of b. And if you were to find the slope would just be the y values subtracted minus the corresponding x values. So that's where I got that from, okay? Okay, so your mean value theorem guarantees when your A rock equals your I rock. Mean means average, okay? Or when your secant line is parallel to your tangent line. Okay? Now, when is this possible? And this is where you guys have to tune in. Mean value theorem is just like the other ones. Okay? F has to be continuous on a closed interval a to b, but there's also a second condition. Okay? So notice how right away that f pretty much always has to be continuous. Okay? But the mean value theorem has an extra second condition. F has to be differentiable on an open interval AB. And again, I could explain that to you guys, but for the sake of time, we're going to go ahead and skip that part, okay? So notice how mean value theorem starts talking about differentiability or derivatives, if you want. Okay? So if these two conditions are met, if you know that the function is continuous and differentiable, you know that you're guaranteed at least one moment. Okay? Cool. Now, here's the last one. Rolle's theorem. Okay? So far we have IVT, EVT, MVT, and Rolle's. IVT, EVT, MVT, Rolle's. You kind of have to say it a few times, okay? IVT, EVT, MVT, Rolle's. Rolle's theorem is really not a fourth theorem. It's just a special case of the mean value theorem. So I'm going to go ahead and write that here. This is just a special case of MVT. And you guys will know exactly what I mean by that, okay? So since this is a special case, okay, these two conditions are going to transfer over. So we need to know that f is continuous on a closed interval a to b, but also it has to be differentiable on an open interval a to b. So let me go and highlight that just so you can see the common trends here. Notice how pretty much all functions have to be continuous on a closed interval in order for you to even consider it. Okay? Now for MVT and Rolle's, you actually need a second condition, which is that f has to be differentiable as well on an open interval a to b. Okay? Now Rolle's actually has a third case here, which is f of a is equal to f of b. I'll go ahead and put that in pink. All right? Now I want you guys to think about this. F of a is equal to f of b. Okay? We saw this notation right here. F of a and f of b, right? If, for example, if f of a was equal to f of b, what would happen if you were to subtract these two values? Go ahead and pause if you need to think about it. Press play when you're ready. If we knew that f of a was equal to f of b, this part up here would come out to 0. Because if you're subtracting the same value, you will get 0. And 0 over anything will give you 0, which is basically Rolle's theorem. This basically tells you that the derivative, there's at least one moment where the derivative will come out to 0. So it's not really a fourth theorem. It's an extension of the mean value theorem. And I'll show you a picture here just to show you what I mean. Now we said f of a is equal to f of b, right? Let's take a look back up here with our 2 points. if these are equal, graphically, what does that mean, right? So I'm going to show you that real quick. And it makes a lot of sense when we draw a picture. If we want to draw a graph that's continuous and differentiable, but also f of a is equal to f of b, we're saying that f of a and f of b are equal so that the two y values are equal, which means, so for instance, if this is a f of a and this is b f of b, I know it's a little abstract here, but they're going to equal, right? So think about what the slope of that line would be if I were to connect these two. What would the A rock be? Right? If you have a horizontal line, right, the slope will always be 0. Well, the mean value theorem states that there's got to be at least one other moment where the derivative will be the same. But in this case, we know the derivative, or I rock, has to come out to 0 as well. Or in this case, we use f prime of c. I'll show you how we use all of these in a problem. The most typical one that you'll see in the AP exam. Okay? So that's basically our 4 theorems. So here's what you guys have to think about. If they only state that f is continuous, which theorems can apply? Okay? I'm going to say that question one more time and I want you to pause, okay? If the problem only states that the function is continuous on a closed interval, which theorems apply? Okay, so if it's only mentioned that f is continuous on a closed interval a to b, you're only allowed to use or apply IVT and EVT. Okay? You can't use MVT or rolls because I did not mention anything about differentiability. Okay? Now, if the problem extends and says, well, f is also differentiable on an open interval a to b, then you start thinking about the mean value theorem or Rolle's theorem. Okay? The rule is the moment they start talking about derivatives, that's where you want to think about these 2 theorems right here. Okay? So here's your little cheat sheet. Okay? And again, it's not the most formal way of writing it, but it'll get you guys to remember it. Okay? So intermediate value is your birth height. You're hitting all values in between. Extreme value theorem is the high and the low. Mean value theorem is where A rock equals I rock. And Rolle's theorem is just a special MVT, where you know the I rock comes out to 0. All right? Okay, so a few things before I show you my one problem, okay? Let's refresh. Continuity is very informally where you don't lift up your pencil. Right? If you're drawing something that is continuously on your paper without lifting up your pen, you know it's going to be continuous. But I encourage you to go back and look at the 3 conditions, okay? Differentiability, there are 3 types of occasions where it's not differentiable. I'm going to have you guys pause here and look back, okay? Come up with 3 scenarios where a function may not be differentiable. Press play whenever you're ready, or if you can't find it. Okay, the most common one is if you have a corner or a cusp. Basically, a corner is when you have a sharp turn in your function, something like this, or pretty much a drastic change in direction. Okay, a parabola is not a drastic change because it's very smooth. Okay, but when you have a sharp change, it's not differentiable right there because tangent lines are supposed to be unique. And if you notice right here, I can draw an infinite amount of ways of drawing a tangent line. All right. Okay. Second one here is at a discontinuity. If something is discontinuous, there's no way of drawing a tangent line there. Okay? And the last one is a vertical tangent. I'll draw you a scenario here. If you had something that looks like this, you could actually draw a tangent line like this, but notice how that tangent line is vertical. The reason why you can't have a vertical tangent line because vertical lines have no slope. It's undefined. Okay? But we'll get to that a little bit later when we actually need to, okay? Here's one thing I need you guys to know. Very important. If a function is differentiable, then the function is continuous. But note, not the other way around. Okay? Don't write this part down. But if f is continuous, then f is differentiable. This is not true. So what this is saying is if you draw any continuous function, is it always differentiable? And the short answer is no, right? Because the most common example is think about an absolute value. It's continuous, but it's not differentiable right there at that corner. Okay? So what we mathematicians like to do is to shorthand things, okay? You guys want to remember this very simple phrase, if D, then C. If something is differentiable, then it's also continuous. But not the other way around. If D, then C. And I'll show you how we use that, okay? So here's here was your PDF that I sent you guys, right? They give you a formal statement, but they also kind of give you like a translation of it, okay? Feel free to look through it. Yeah, it's there for you guys, okay? Notice how the average rate of change here, there's at least one moment where IROC will be parallel or equal to it in slope, all right? That's just for you guys to have as a reference. But let's get to an example. Here's the most common way that you'll see these four theorems, okay? So I have this one example for you guys. Write it very clearly, everything in purple and blue and red, I guess. But go ahead and press play whenever you're ready. Okay, so here it says let f be differentiable on a closed interval from 0 to 6. Given the table of values of f, answer the following, okay? So we have this table, and I'm going to give you guys a series of questions, okay? Here's our first question. What is the least amount of times f will cross the x-axis? Okay, write that down. Okay, so first off, whenever they ask you, is it possible or how many times will this happen, you always want to think of existence theorems, okay? How many times or what is the least amount or is it possible, all right? Right away, you're thinking about your four existence theorems, okay? So the first thing you want to do is you want to identify what's given. You have to look at the facts here. They tell you that f is differentiable on a closed interval, okay, which is way better than an open interval. Okay, if it's differentiable on a closed interval, it's definitely differentiable on the open interval as well. Okay, because closed interval just includes more, right? So remember that one fact I gave you. If they tell you that something is differentiable, it's also implied that f is continuous on a closed interval. So they don't have to say it. You have to understand that they kind of gave that to you. Okay, replay that if you guys need to. Okay, so knowing that we have these two facts here, what theorems come into play? So right away, IVT can apply, EVT can apply, and MBT can apply. Rolle's theorem, we're not quite sure yet if that third condition is met, but it could happen, okay? So right now, we're looking at least at the first three. So here we go. What is the least amount of times f will cross the x-axis? Okay. You have these values. So at 0, I'm not gonna graph this all out, but I'll give you a rough drawing of it. We only know these 7 points. We don't know what happens in between, but we do know it's continuous and differentiable. So for instance, 0, 5, and I'm really eyeballing this, you guys. 0, 5, 1, negative 2, 2, 8, 3, 5, 4, negative 3, 5, 9, and 6, 8. Now, you wouldn't be drawing this out, but I'm giving you guys a scenario here, okay? We don't know what happens in between these graphs, but we do know that they're continuous, meaning that we don't lift up our pencil. So here's one iteration of what it could look like, okay? Okay, so let's read our question now. What is the least amount of times f will cross the x-axis? Okay, so think about what it means when it touches the x-axis. That's telling you that f of x will equal 0 because by definition, I'll use a different color. These are your roots or your x-intercepts or your solutions, right? Now, I wouldn't use the picture to answer the question. I just want you to think about this here. How will you know just by looking at the table when it will cross the x-axis? It's not too obvious, but you guys have what it takes to answer this question. So really think about this here. How do you know just by looking at the values when it will cross the x-axis? Press play whenever you're ready. We're going to know when this graph will cross the x-axis whenever there's a sign change in the y values. So for instance, if you look at the red values here, starting at 0, you were at 5, and at 1, you went to negative 2. So somewhere in between 0 and 1, you would have eventually went from 5 and then crossed through a 0. Okay? So a sign change indicates that there's going to be a 0 in between. So how often do we have sign changes here? We have one here, between here, between 5 and negative 3, and negative 3 and 9. I counted 4 different moments here, okay? And it happens to illustrate that on the picture. Again, I would not draw out the picture, okay? That's not good enough justification. So here's how you guys would say it. You would say 4. By the intermediate value theorem, okay, f will cross the x-axis, and this is where it's important, somewhere between 0 and 1, 1 and 2, 3 and 4, and the interval 4 and 5. We don't know exactly where the 0 happens, but we know that it happens somewhere in between these intervals. Okay? Now, this graph could have crossed the x-axis billions of times because we don't know exactly what happens in between. For instance, from 0 to 1, this graph could have decided to go through the x-axis 6 times, but we don't know that. And that's why they use the word least right here, okay? So there's an example of IVT. Let's try another one here. Same problem. Don't write it again. Here's the part B. What's the least amount of times f of x will equal 6? So use that same logic here, okay? When will you get 6? Answer this on your own, and then press play whenever you're ready. Okay? So the answer here is 3. All right? By IVT. F of x will equal 6. Somewhere, I should say somewhere in between. Somewhere in between here, because from -2 to 8, you eventually have to cross 6. From 8 to 5, you eventually have to cross 6. Same thing here. So the intervals are from 1 to 2. 2 to 3, and 4 to 5. Okay, hopefully you got that too. If you didn't, let me know. All right, here's part C. Different phrasing, okay? So I'm going to give you a statement. You have to tell me if it's always, sometimes, or never true. So here they're saying that given f of x will equal -1. Always, sometimes, or never true. Okay? Press play whenever you're ready. The y value will eventually hit -1. Okay, this is definitely always. Okay? For instance, right here, traveling from 5 to -2, you will definitely have to hit -1. Okay? So that's always true. Okay? Here's another one. F of x equals 38. Okay, always, sometimes, or never true. Press play whenever you're ready. Pause and really think about it. Take all the time you guys need. Okay, in this case, this would be sometimes. Okay, now first off, always wouldn't work because based on the table values here, you're never in between to get 38, okay? But sometimes it is a possibility because for all you guys know, at 0.5, it went to 38, right? It could happen, which is different from saying that it can't happen. Okay? It is a possibility, but we can't say that it always will happen. All right? So the sometimes is a little tricky. Let's do another one. Okay. So part E here says f has an absolute max somewhere in between 0 to 6. Always, sometimes, or never true. Press play whenever you're ready. Okay, in this case, since the function is continuous from 0 to 6, f is guaranteed to have an absolute max by EVT. Okay? Now here's a little modification of it. Here's part F. Same thing, always, sometimes, or never true. F has an absolute minimum of -3. Go ahead and answer that there. Okay, this one here is actually sometimes. Okay, now if you put always, I'll explain why it can't be always, okay? Same reasoning for that last example, I think in part D. At 2.5, f of x was at -5,000. So that could have happened, right? So that means the absolute minimum is not -3. It's not the lowest value, right? Now, it could be that -3 is the lowest value, but it's not guaranteed. So we can say that it's plausible, but not guaranteed. All right. Just another one, just so that you guys understand like what the difference is between always, sometimes, or never. Okay. Here's another statement. F has an absolute max of 5. Okay, is this always, sometimes, or never true? Okay, this one here is never, because I can prove it wrong right here. Look at that. We already have values that are higher than 5, so I know that 5 can never be the absolute maximum. So you have 3 cases here of always, sometimes, or never. Okay, and you'll get more practice with this on Delta Math as well, okay? Okay. Oh, one thing before I move on to the last few. If your problem does not state that the function is continuous or differentiable, you got to be mindful of that. If they do not make a statement of it, you cannot apply the theorems, okay? Delta Math gets a little bit tricky with that. Here's part H. Does there exist a C somewhere between 0 and 6 such that f prime of C equals -1? Go ahead and write that down. Okay, what you guys need to train yourselves to do, because we're getting closer to the AP exam, okay? The moment, notice how it says, does there exist, or is it possible, right? The moment they talk anything derivative, what theorems are you going to think about, right? The moment they talk about derivatives, you're either thinking about MVT or rolls. I know this is not rolls because the derivative is supposed to come out to 0, and this is -1. So this is a case of MVT here. And this is probably the trickiest one, okay? So we know that the function is differentiable and continuous, so we know MVT can apply. This is where f of b minus f of a all over b minus a equals f prime of c. And this is where it gets a little tricky. They ask you, does there exist a c such that the derivative comes out to -1? So what you got to do here is you have to find out the average rate of change between 2 points that'll make it come out to -1. And this is where it takes a little bit of practice, okay? So here's what I noticed. I noticed that all of the x coordinates travel by 1s. So if I pick 3 and 4, or 4 and 5, or 2 and 3, that bottom part will always come out to 1. So that's easy to do. Okay? So how will I get a -1? So I notice right here, just so you guys can get an example of it, if I look at these 2 points, and I'll write it out, 5, 9, and 6, 8, if I find the average rate of change there, that's 8 minus 9 over 6 minus 5, that's actually -1. So my answer would be yes, somewhere in between 5 and 6 by MVT. Okay? So sometimes the points are right next to each other. Sometimes you gotta look at all the combinations. Okay? So for instance, here's one to practice. Same wording. Does there exist a C somewhere in 0 to 6 such that f prime of C equals -3? Can you find 2 points where the slope would come out to -3? Pause here and really think about it. Okay, so to get a slope of -3, I need to find 2 points where the slope would come out to -3. So I noticed that that would work right here. And sometimes there's more than one answer, you guys, okay? Because I noticed that 5 and the 8, 5 minus 8 will give me the -3, and 3 minus 2 will give me the 1. So we'll say yes. Somewhere in between 2 to 3 by the mean value theorem. Okay? Now here is, I think this is my last one. Yeah, this is my last one. What is the least amount of times f prime of c will equal 0? Okay, so remember, when you see derivatives, you think of either MVT or rolls, but in this case, the derivative comes out to 0. So that implies that we're thinking about rolls here, okay? Remember, Rolle's theorem, I'll scoot back real quick. Rolle's theorem stated that if the function is continuous, differentiable, and the two y values are the same, right? You know your average rate of change will come out to 0. All right? So here we go. What you want to do here is you want to look at the table. Are there moments where the y values are the same? Okay, so I'll give you one. I noticed that right here we have two of the same y values, right, at 0 and at 3. So I know somewhere in between 0 and 3, there's a derivative that also comes out to 0. Okay, so from 0 to 3. Now, is there any other moment where the derivative will come out to 0? If you notice right here, there are two y values of 8 between 2 and 6. So I know somewhere between 2 and 6, there's also another derivative that's equal to 0. So here I counted 2 times. There's two different cases by Rolle's theorem here. So somewhere in between 0 and 3, I know the derivative will come out to 0. And somewhere between 2 and 6, I know the derivative will come out to 0. We don't really care where it happens. We're just proving that it exists, which is why we call it the existence theorem, okay? Practice this, you guys. We will have more practice when we get into AP Prep, but this is pretty much what you will always see, okay? So review it as much as you can, and then go ahead and practice off on Delta Math, all right?